platform for modeling of algebraic behavior, experience, and conclusions. So, the current stage of development of the software system industry is characterized by a significant complication of the process of their development. Today are widely used cyber-physical systems, blockchain technologies, and in particular smart contracts, distributed ledger technology, and other. Typically, cyber-physical systems are the system with a critical application area. Therefore, when designing such system, increased demands are placed on their reliability and safety. When we say about distributed ledger technology, we also say about blockchain. So, accordingly, like as a new technology, blockchain has its own vulnerabilities. Thus, all algorithms that are used require the careful analysis and verification, namely the checking the stability of the system against various attacks such as double spending attacks, greeting attacks, transaction denial attacks, desynchronization attacks, and others. At the same time, the existing methods of quality control of the developed system are characterized by incompleteness, high complexity, and insufficient reliability. This situation inevitably intensifies and increases the number of errors of the development of systems. As a rule, an analysis of the competence of the system with requirements that are imposed on it is carried out either by means of its visual analyzing or by a testing method. However, if any of the properties of the system can be formally expressed, for example in the form of a formula of mathematical logic, then the analysis of this property can be carried out by verification methods. As a rule, verification is used to analyze the first requirement to the system, its correctness. Note that this requirement is main one. So the main idea of our presentation is to describe the special platform for modeling of algebraic behavior and also present a few examples of implemented models. So the main components of the platform about what we say today is algebraic program systems. The main goal of the system is to create an algebraic program that solves mathematical problems. APS include proving and solving systems. It was developed by the Algebraic Institute of Cybernetics of the National Academy of Science of Ukraine. It was the first systems of term rewriting which used the systems of rewriting rules as rewriting strategies separately. A proving system gives us a possibility to prove some trueness of a formula in a theory of the axioms and relations are given. Further, resolving equations in solving systems in algebraic program system are implemented the following theories: enumerated type theory, Boolean logic, linear arithmetic, float arithmetic, string solving, and other. The next component of the system is insertion modeling systems. Insertion modeling system is an environment for the development of insertion machines used to represent insertion models of distributed systems. Insertion modeling focuses on building of models and studying the interaction of the agents and environments in complex distributed multi-agent system. The main notions of IMS is the insertion function, which defines the behaviors of agent and actions of environments. We used the behavior algebra specification for the formalization for the insertion modeling method, and the deductive of symbolic method in IMS based on the such external provers and solvers as Pressburger Omega, Fourier-Morsky in real life, this is our tool, and CVC3, Z3, and MASH-Z. The next component is the algebraic engineer. An algebraic engineer is an algebraic tool for modeling of system behavior. Is created on the basis of the IMS system. It has the following features: generation of symbolic behavior scenarios, resolves the problem of reachability of some property such as safety, liveness, and security violations. It detects the reachability of a property given as a formula and given as behavior in a behavioral algebraic expression. Provide verification by symbolic modeling of protocols, programs, models, and other behavior specification given in behavioral algebraic expression, and map symbolic modeling to original language specification. And the latest component is SimTech platform. SimTech platform is a system which uses symbolic technology which involves algebraic and deductive formal methods for the resolution of sophisticated industrial challenges. The main features of SimTech platform are testing technologies, model-driven development, support of the development process of a critical systems or system with quality of service, verification and validation, cybersecurity. On this slide, we present the main windows of this platform. After creating new project, we see following arrangement of menus and windows. Horizontal menu gives user possibilities to make some manipulation with a project, such as back to previous and next action, create, save, start, copy, export or import of project, creation of different experiment with a model, creation of copy of experiment. Vertical menu. In this menu, we see the list of items that are the key definition of formalization and are the basis for model formalization, and also a list of special platform tools. As you can see, the main workspace is occupied by such windows as Protocol, Behavior, Console, and Act. In these windows, after creation, will be displayed the key elements of the model, startup results in console, and other. We also will use them to edit and describe the necessary elements. Let's consider the main functionality of the platform on the concrete examples. For this, we describe the model of how a coffee machine works. We have an automated machine which interacts with the external environment by means of coins, input data, of certain denomination and two buttons, make coffee and cancel. Requirements for the operation of a coffee machine are given below. So, the first step is to add agent types and agent attributes. In the vertical menu, we see the items agent types. In that, we can add types of agents. After that, we can choose the needed agent type. And in the special window, we can add agent attributes. After the finishing of the description of agent types, we must add the instance of agents. In our example is only one agent. The agent name is CoffeeMesh1 and its type is Coffee Machine. The next step is to determine all trigger events. Requirements 3, 4, and 5 describe the reaction of the agent to exposures in the environment. They explicitly define trigger events: insert coins, press button, make drink, push button, return of the sum. All basic protocols are presented in the list of basic protocols in the vertical menu. Any of them must be described on the special tab Basic Protocols. Their MSC diagrams must be described on this tab too. So we have the list of basic protocols and some example of the basic protocol insert coins. Initial environment. In the initial environment, we describe the initial values of our model. Behavior. Requirements do not clearly define a certain sequence of application of basic protocols. Initially, only the third protocol can be applied and the rest after including itself. After the fourth protocols, it is possible to repeat preparation of new portion of drink or complete operation. This sequence is present in the form of the following UCM diagram. This diagram you see also on this slide, and we see the process of coffee machine work. The reflection of UCM notation in a text form must be written in the tab text. After starting of a program of trace symbol generation, we get a result where the behavior of a model is represented by 18 traces. Also, we have a few projects that was developed on this platform. The first of them is Skylonomi project. Skylonomi project is an educational online platform that tokenizes productive activities in the learning process and is focused on gaining monetized online knowledge and skills. The Skylonomi ecosystem is built around an IT platform that allows participants to effectively build and administrate the relationships that are related to training, investing, and sharing experience. Developing the Skylonomi project required a set of central functions of the blockchain for ensuring a stable and efficient system that works. The main purposes of the tokenomics model formalization of the Skylonomi project are the search for modeling errors such as finding failings or possible contradictions. The search for effective scenarios for the system in the model and other, the possibilities for analyzing and predicting the model, and the possibilities for analyzing the feasibility of project financing. The project of the formalization of the tokenomic project consists of the following steps: selection of the agents and definition of their attributes corresponding to the level of abstraction demanded, definition of agents' actions, and deciding of agents' behavior. As a result of the simulation of model and with the selection of different values of attributes, we were able to analyze the behavior of the Skylonomi model according to different Bitcoin strengths. On this slide, you see one of the example of result that we get after the simulation of specific model by this. The next project is the cybersecurity project. The algebraic approach in cybersecurity was demanded over the past 2 decades with the appearance of the efficient solving and deductive tools. Different techniques like symbolic modeling and consolic computations are used. The algebraic approach that has created more possibilities for methods of detection in cybersecurity. Our tools anticipate algebraic matching in different models. The following applications are available and are under active research. The first of them is definition of attacker behavior, and the second is vulnerabilities detection. And the next example is the text code. We considered the subset of text code and created its formalization that contains all articles belonging to value-added tags and its dependencies from additional bylaws. For presentation of algebraic model, we use double-sort algebra that contains the algebra of behavior and logical language with arithmetic, set theories, and logic operations. Formulas of this language are constructed from operation and predicates, our integer real, enumerated, and symbolic types. Usually in tax code we have two kinds of agents that are tax player and taxation office. We can consider the set of tax players that interact with each other. The given approach could be applied to legal requirements that could be formalized by such manner. We can watch the possible scenarios and analyze the environment and system to achieve the right formal presentation. The traces were verified by third person with economics background and corresponding correctness were made. Now the digital tax code of Ukraine is ready for use in the scope of algebraic program systems and could be developed in interesting organization. Behavioral algebra and basic protocol specification are used for the formal description of a model. Algebraic artifacts such as theorems and abstract algorithms provide a basic for formal verification methods. These methods were implemented and successfully applied to the industry projects in Motorola and others. Formal verification anticipates the checking of the properties of the system. The properties could be classic, but such as absence of deadlocks and non-determinisms of subset domains specific define safety of or liveness condition. We can prove the reachability of demanded properties by using a symbolic modeling method developed in the scope of insertion modeling system. The given approach could be applied to models that could be formalized by such manner. One of the difficulties is the process of formalization. Due to the experience that should be two specialists involved in the process of the formalization, algebraists and specialists in the specific area of the project.